Bismillahirrahmanirrahim. In this video and in some upcoming videos, we will discuss the field-oriented control of the induction motor. In the field-oriented control of the induction motor, we operate our induction motor like a separately excited DC machine. In the separately excited DC machine, your armature flux and the field flux are decoupled, means they are orthogonal and they do not depend upon each other. That's why we say the armature flux and the field flux are decoupled. However, if you want to increase the flux in the field winding, you can control it with the help of the current in the field winding. So if I consider the field current IF, with the increase of this field current IF, the flux in your field winding will be increasing. So the relationship between field current and the field flux can be shown like that if you will be increasing the field current, the flux will be increasing. But once the saturation of the material starts, then with the increase of the field current, there will be no increase in the field flux. So this is said to be the saturation. So we will be discussing the operation of the machine in the linear region, in which your field current can directly control the field flux. Similarly, you can define the behavior of the armature current and the armature flux. Now if you look at the construction of the machine, here you can see these are the pole shoes, and the field winding is placed over these pole shoes. So let's suppose that this is the field winding which is placed over here. So the purpose of the field winding is to generate the main flux in the DC machine. So let's suppose that the direction of the current in this winding is like this, and because of that the flux by applying the right hand rule will be in this direction. So here you can see the magnetic lines of forces, and as these pole shoes are curved and the distance between the armature and the pole shoes is constant, so magnetic lines of forces will be perpendicular to the surface of the armature. So magnetic lines of forces always takes the path of the minimum reluctance, and reluctance depends upon the length. So these magnetic lines of forces will be traveling perpendicular to the surface of the armature, and then will be traveling at the minimum reluctance path, and when they will be coming out of the armature to reach to the next pole, they will adopt the path of the minimum reluctance, so they will be perpendicular to the surface. So now if you consider any point over here, let's suppose at certain instant of time your armature conductors are like this, and let's assume that the current in this is going into the paper, and from here the current is coming out. So I'm going to mark it cross and dot. So if you look at the direction of the armature flux, so direction of the armature flux will be like that by applying the right hand rule, that will be perpendicular to the surface which is formed by this loop of the armature, this loop. So if you now look at the flux because of the field winding, that is, let's suppose phi f, and this is the flux because of the armature winding, so both of them are perpendicular. Similarly, if you consider this armature loop over here, and if you consider the current over here and cross and dot, so armature flux will be in the upward direction, and over here if you look at with respect to the phi f, so again they are perpendicular, and you can say these are orthogonal and decoupled. Okay, so at any instant of time, because of this construction in the DC motor, your armature flux and the field flux are perpendicular to each other, right? So how you represent the torque in the DC machine? The torque is given as equal to kT into IF into IA. Basically you have the expression like that torque is equal to some constant kT into flux in the armature and the flux of your field winding, because basically the torque is the cross product of the armature and the field flux. So from there we are going to get this expression. The torque depends upon the flux in the field winding and the armature winding. If the flux will be increasing, the more force will be applied on the conductors of the armature. So when more force is applied, it means the more torque is going to be there. So The torque is given by this expression, but we can relate field current with the field flux. So with some constant we can say that phi f is equal to if, and similarly the armature flux will be related with the armature current. So here you can see the modified constant kt, which is accommodating the constants which are relating flux with the current, right? So I can write it like that, that field flux is equal to some constant into if, and similarly armature flux is equal to some constant into ia. So taking those constants over here, so this is the modified constant kt. So the torque in your dc machine is given by this equation, that is the product of the armature current and the field current. So the construction of a DC machine is such that the field flux produced by the current IF is perpendicular to the armature flux phi A that we have seen over here. The armature flux and the field flux. So they are perpendicular to each other. So because of that, we can say that the armature flux and the field flux are orthogonal or decoupled in nature. They are not going to affect each other. If you will be changing the armature flux by changing the current IA, so it is not going to affect the flux in this direction, because it will not be having any component in this direction, right? So this means that when the torque is controlled by controlling the armature current, if you control the torque with the help of this one, the flux phi f, this one is not affected. If you are changing this one armature current, this will not be affected, right? So similarly, if I say that if I am changing if to control the flux in the field winding, this will not be changing the flux of the armature winding. So because of this decoupling, when the field current if is controlled, it affects the phi f only but does not affect the armature flux. Or we say that if we change the armature flux, your field flux does not change, that remains constant. So these are decoupled. So the machine torque, the torque of the DC motor is given by this expression, that is equal to kt phi f into phi a, that can be written as in kt prime ia into if. Okay, so the armature current is basically called the torque control component. Why? Because as I told you, that major power is delivered by the armature circuit. Armature current is quite high as compared to your field current normally in the separately excited DC machine, because the function of this flux is just to establish the flux linkage and to have the force that is acting on these armature conductors so that they are rotating. So when the rotation starts, the major power is extracted from the armature source. So armature current is significant as compared to field current, and field winding resistance is usually high as compared to your armature winding resistance, because the armature is going to carry a bulk amount of current. So its dissipation and the voltage drop in the armature winding should be as small as possible. So the armature winding is made up of thick copper and its resistance is usually very small. However, the field winding resistance is large as compared to your armature winding. Okay, so the armature power is the significant power in the case of the DC machine. So the torque of your the torque which is generated by your machine or which is provided to the load by your DC machine is basically controlled by the armature current. So armature current is said to be the torque component. However, the field component is also required, but this current is usually very small. So its contribution in the induced torque is small, or in the electromagnetic torque is small. The contribution of the armature current is significant, highly significant as compared to the field component, that is the IF. So the armature current is usually used to control the torque of your machine, and the field current can be used, but its impact will be small as compared to your armature flux. So in a DC motor, we can say that we have two currents, field current and the armature currents, and those are separately controlled to control the torque of your machine. The field winding current is controlled with the help of the converter that is connected over here, a DC to DC converter or the controllable voltage source. controlling the current in this field winding, and similarly you have the power electronic converter over here, which is controlling the voltage across the armature terminal and controlling the current in this and controlling the torque of your machine. So armature current and the field current both are independent of each other because these are orthogonal, and both of them can be used to control the torque of your machine. So you have two separate controls, the field current control and the armature current control. Now if we look at the induction motor, so in the case of induction motor, you have the current in the stator, and if I represent it in the three phase, so you have the three phase supply to your induction motor and you have the stator current. There is no control of the rotor side. Specifically in the case of the squirrel cage induction motor, you do not have access to the rotor. Your rotor is short circuited, so you have only access to the stator of your machine. So the stator current will have to do two functions. If you want to compare it with the DC motor, in the DC motor we have the armature current, we have the field current, and we are going to provide separate field and the armature source. But over here we have only one source, right? Three phase source on the stator side of your squirrel cage induction machine, and the current which is drawn by the stator from the source is responsible for the generation of the rotor flux and as well as the armature flux, right? So there is the flux linkage between the stator and the rotor, and the stator current will be responsible to perform both of the actions, the rotor flux and the armature flux. So there is the coupling between armature flux and the field flux in the case of the induction motor. So if we want to operate it as a DC motor, what we will have to do, we will have to identify that which component of the current is performing the action of the rotor flux and which component is going to perform the action of the stator flux if we compare it with the DC motor. Okay, so if we represent our stator current in the form of the space vector, let's suppose that it is somewhat like this. The stator current Is, we have already studied in the previous videos that we can transform that three phase current set of currents, phase A and phase B and phase C currents, into the rotating frame of reference that is represented as the QD frame of reference. That may be the stationary, that may be the that may be rotating with the rotor speed or may be rotating with the synchronous speed. So over here, if we assume that we have the frame of reference that is rotating with the speed omega e, and omega e is representing the synchronous speed of your induction motor, right? And that depends upon the frequency. If I talk in terms of RPM, so this is 120 F by P. So this omega e is representing the speed of the stator magnetic field. So your current phasor or the space vector will be rotating at that speed. So it will be having two components. One component will be along q axis and the other component will be along d axis. So the d axis component of the stator current, let's suppose that it is in the direction of the rotor flux, or it is responsible for the flux that is being generated or being developed in the rotor side. And the other component of the current, it is IQS, that is responsible for the generation of the torque from the stator side. So over here, if you look at this one, over here we have the armature current and this one is the field current. Both are orthogonal to each other. So if I want to develop the analogy, I can say that this part is representing the armature flux and this part is representing the rotor flux. So this component of the current, that is IQS, that is going to contribute majorly towards the torque, because over here we have seen that phi A is controlled by the IA and IA is the torque component. So similarly over here we are going to say that is IQS is the torque component and this IDS is basically the flux component of your stator current. So if we represent our stator current in the DQ frame of reference, in a rotating frame of reference, those we have discussed in the previous videos. So one component of the stator current, that is the Q component, can be considered as the torque component, or like the DC motor, and the D component will be considered as the flux component, just like your DC machine, right? So the equation for the torque of your induction machine can be written like that. Considering this frame of reference, the torque is equal to Kt into phi r into IQS, right? So this rotor flux is developed by this D component of the stator current. So this will be called the field component, and this IQS, or you can say, if I just compare it over here, that armature flux. So armature flux component will be basically controlled by this IQS, and that is basically the torque component, because by the major control of the torque will be achieved by this one. So now onward we will be considering IQS as the torque control component, and we will be considering IDS as the field control component in the case of the induction motor, right? And how to control the torque and the flux? You will have to control the current in your induction machine, and that is controlled with the help of the inverter. That may be a space vector PWM based inverter, or sinusoidal PWM inverter, any inverter that will be basically controlling the current that is injected in the machine, and that current is synthesized for using these references in such a way that these components IQS and the IDS control the torque, and they are going to provide you the same behavior as that of your DC motor if you compare. Because if you look at this one, IQS is controlling the torque component. If you want to control the torque, you will be controlling the IQS only, and you will be controlling your stator current in such a way that only the Q component is changed. D component does not change. If D component is not going to change, so your rotor flux will remain constant, that will not be affected. And similarly, if you want to control the rotor flux, you will only be changing the D component of your current, and you will keep the Q component of your current constant. So you will be controlling this stator current in such a way that only one component is affected and the other one is not changed. So you can have the decoupled effect, that when you will be changing this IQS, this IDS is kept constant. So you can say when we are changing the torque, the rotor flux will be kept constant. And similarly, if you are controlling IDS, you are controlling the stator current in such a way that only IDS is going to change, so only the rotor flux will be affected and the torque will not be changed. So now let's look at this with the help of the diagram, that how we can control the stator current like this. Okay, now look at this diagram, the phasor diagram. So that can be easily understood with the help of the equivalent circuit of your induction motor in the steady state. This is the stator side, and this one is the rotor side, and this one is your magnetization branch. So if I say that this stator voltage is applied, and this is the stator current, so this current will be divided into two parts at this point. Some current will go through the magnetization branch, and some part will go towards the rotor side. So if we consider it at the phasor current IS, okay. So basically it will be having two components, the D component and the Q component. So as we have seen before, that the D component is basically the component which is responsible for the rotor flux. So we are going to say that this D component will be passing through the magnetization branch. This IDS is the current through the magnetization branch, because it is representing the flux linkage between stator and the rotor, and will be responsible for the rotor flux. So phi r, it is equal to this phi m. Phi m is the flux of this magnetization branch. So this is basically the rotor flux. So this component of the current IDS, which is passing through this one, is the flux component, and the component which is passing through this part, that is through the rotor resistance RR by S, that is responsible for the torque, right? Okay, now if we say that the voltage at this point is equal to Vm, so let me use a different marker. If the voltage at this point is Vm, And as this is the purely inductive branch, so what about the current? This current IDS should be lagging behind by the angle of 90 degree. So if we consider this Vm as the reference that you can see over here, so your IDS will be lagging behind by the angle of 90 degree with respect to the voltage across this branch. Okay, now let's assume that our stator current is somewhere over here at a certain instant of time. This is the stator current Is, right? So it will be having two component, one component along the q axis and the one component along the d axis. Over here you can see that the voltage is considered aligned along the q axis, right? So let me represent it over here. This is our q axis and this one is our d axis. So the voltage across the magnetization branch Vm is considered as the aligned with the q axis over here. And with respect to that, if you look at the IDS will be along the d axis, right? Because it should lag behind by the angle of 90 degree, considering that this is the pure inductance. So in the inductor, the current lags behind the voltage by the angle of 90 degree. Now if I look at this current, the stator current Is, so it will be having two component, one component along the q axis, that is Iqs, and the other component along the d axis, that is Ids, in the let's suppose rotating frame of reference that is rotating with the speed omega e, that is the synchronous speed. Okay, so this component IDS is responsible for the rotor flux or the flux of this branch, that is the magnetization branch. So that's why we are going to say phi r and phi m. So the flux of these two will be in the direction of these currents. So rotor flux and the magnetization flux will be represented like this. Okay, now if you add the voltage drop across this one with this magnetization branch voltage, this is Vm, so this is the voltage drop. So the stator voltage will be slightly leading the magnetization branch voltage. So that's why you can see the stator voltage is shown over here at a certain angle, let's suppose theta 1, with respect to the Vm, right? So let me mark it theta 1. So stator voltage is slightly leading the magnetization branch voltage by theta 1. Okay, so now if I want to change only the q component, keeping the d component constant, so I can set this stator current to this position. So if you will setting it to this position, here you can see what about the d component, that is not changed. Whatever is the d component of this vector, same is the d component of this vector. So d component is same. However, if you look at the q component of this stator current Is prime, so q component is this one. But if I change the stator phasor to this position, over here you can see the q component is changed, right? So the concept over here is that if you synthesize the stator phasor in such a way that it is changed from this position to this one, so the d component will remain same, the q component will be changed only, the torque component will be changed, the flux component will remain same, right? So it means you can control the torque independently as compared to your phi r and phi m, because this component IDS is responsible for this rotor flux or the magnetization flux, and we are not changing that one even though we have changed the stator current. Only the q component is changed, that will change the torque and the flux will remain unchanged. So here we can say we have the decoupling. We can position our stator current such that, let's suppose over here again the d component will remain same, the q component will get changed. So we can position our stator current in this rotating frame of reference QE and the DE such that only the q component is going to change and the d component is going to remain constant. Now let's look at that how we can change the D component keeping the Q component constant. So now let's look at this diagram. Here we have seen that we can control the current of the induction motor, and we can control the torque and the flux independently. But for that we will have to decide what should be the D component, what should be the Q component, and then we will position our stator current vector in the Q D frame of reference that is rotating at the speed omega e. So by constructing that stator vector over here, that you can see, you can position it over here, you can position it over here, you can control the Q component, you can keep the D component constant, and similarly over here you can keep the Q component constant and you can control the D component. So what should be the D and the Q component for the particular torque and the rotor flux or for the speed? So you will have to decide about that set of the D and Q components, and then you will have to synthesize the stator current, right? And this is done with the help of the vector control, and that is realized by the inverter in your induction machine. So inverter is the most important component from the power electronics point of view, that will be realizing that current in your machine such that you get the decoupled control, and that your torque component and your flux component are orthogonal and the decoupled. And because of this, your vector control is given the different names. It is also called decoupling control, it is also called orthogonal control, or it is also called trans vector control. So different names are given because you are decoupling the torque and the flux over here, right? So now let's look at the diagram which explains the vector control more in depth. So over here we have the reference D and the Q component, and um, that is in the rotating frame of reference, that is rotating with the speed omega e, and then we convert it into the stationary frame of the reference using the transformations. Those we have already discussed in the previous videos. So for those transformations we require this information, cos of theta e and the sine of theta e, where theta e is basically the position of the frame of the reference which is rotating with the speed omega e at certain instant of time. So you can convert them into the stationary frame of reference. Basically you have like that, this q and d which are fixed. In this the speed is 0, speed of the frame of the reference, and you are translating them into a frame of reference, that is this q and d, but this is rotating with the speed omega e, and the vice versa. That is you can translate from the stationary frame to the rotating frame, or from rotating frame to the stationary frame. So these components are in the rotating frame of reference, you are converting into the stationary frame of reference. For that you need the information of cos of theta e and the sine of theta e, because these are required in the transformation matrix that converts from stationary to the rotor frame of reference. So you can convert them into stationary frame of reference, and then from stationary frame of reference you can go into the ABC frame of reference, and you can generate three reference currents IA, IB and IC, which are injected into your induction motor with the help of the inverter. So this activity is done by your inverter, that ensures that a required current is injected in your machine. So inside the machine what you have, you can realize that ABC is converted into the stationary frame of reference, and then from stationary frame of reference the quantities are translated into the rotating frame of reference. And for that we again need this information, cos of theta e and the sine of theta e, that is the speed at which your frame is rotating, that is basically the speed of your stator, and that is defined by the frequency of the stator. And once you convert it into the rotating frame of reference, that is rotating with the speed omega e, then you have the machine model in the DEQE frame of reference that we have already discussed in the previous videos. You can refer to those ones to understand this model in detail, and we can keep our D component aligned with the rotor flux, and the Q component of the stator current that will be controlling the torque, and D component will be controlling the rotor flux, and this frame is rotating at the speed omega e. So we need to have the information of this cos of theta e and the sine of theta e. These are basically, you can say, the unit vectors, unit vector component, and these unit vectors basically performs the transformation right? So in this part you can see you have the inverse transformation, that is you are converting from rotating frame of reference to stationary and from stationary to ABC frame of reference. At the machine terminal, the inverter is injecting those currents, and inside the machine you have the transformations, considering the dynamic model, and then you are going to look at the machine parameters using the model in detail. So this is the control part, and over here you have the machine that is implementing that one. So we are discussing it in the dynamic frame of reference. You know that e raised power j theta, that is equal to cos of theta plus j sine of theta. So this is basically you can say the vector rotation over here, and that is rotated according to this one, right? So how you generate this unit vector, that is controlling the transformation from stationary from rotating to stationary frame, or from stationary frame to rotating frame. Based upon this one, the vector control is divided into two parts, two types. One is called the direct or the feedback method, that was invented by Blaschke for the generation of the cos of theta and the sine of theta for the vector control. And the other method is known as the indirect or the feed forward method, that was invented by the Hesse, and that is also used to generate this cos of theta and the sine of theta, but in a different way. So these methods are different essentially by how the unit vector, this cos of theta e and the sine of theta e, is generated for the control. So the orientation of the IDS with the rotor flux phi r, or the air gap flux phi m, or the stator flux phi s, is possible in the vector control only because of these unit vectors which are generated using the different way. Basically you are looking for the speed of your stator. This is stator speed, right? And because from the stator speed you can get this information of the theta e. So the rate at which this angle theta e is changing is basically going to give you the speed of your stator, or the synchronous speed with respect to the stationary frame of reference, right? So the cos of theta and the sine of theta will be giving you the information how the rotating d and q is making its projection along the stationary q and the d. So this unit vector is very important. So now we will look at the two diagrams, that how we can estimate these unit vectors using the direct method or using the indirect method, and that will clear you the difference between these two techniques. Okay, now look at this diagram. This is indicating the direct vector control. So in the direct vector control, the position vector cos of theta e and the sine of theta e, that is calculated with the help of the voltage that is sensed or measured at the machine terminal, and similarly the current that is being injected into the motor. So the stator voltage and the stator current, those are measured and are given to the machine model. In the next upcoming videos, we will discuss this model in detail, and that model gives us the information of the rotor flux and also tells about cos of theta e and the sine of theta e, where theta e is basically the position of the rotating frame of reference at one particular instant of the time with respect to the stationary frame of reference. So if you are measuring the rotor flux and this unit vector, or you are estimating this unit vector or the rotor flux with the help of the voltage and current information, then this method of the field oriented control is called the direct vector control. So if you look at this diagram, you have the flux command and you have the speed command that is given to this control diagram, and you are estimating or measuring this rotor flux, and you are estimating or measuring this speed. So at the moment we assume that you are measuring these ones. So if you measure this rotor flux and the rotor speed, then you can use the PI controllers over here. This G1 and G2 are representing some controllers over here, and most of the time these will be the PI controllers. And from these PI controllers, using these PI controllers to minimize the error of this flux and the error of the speed, you decide about the D axis current and the Q axis current of the stator, right? And then this d axis and q axis current is converted into the stationary frame of reference. Over here they are in the frame of reference which is rotating with the speed omega e. So you need the voltage vector rotation, that is conversion from dq rotating frame of reference, that is rotating with omega e, to the stationary frame of reference, that is fixed. So once you do this transformation, over here you get the quantities in the stationary frame of reference, and then you can use the inverse Clark's transformation and you can convert the information into the ABC frame of reference. So these are basically the required currents which are to be established in your machine so that you get this rotor flux and this speed. So this set of current which is calculated is given to the inverter control, and then inverter control changes the voltage at the machine terminal with the help of the PWM that is used inside. It may be the space vector PWM, sinusoidal PWM, or any other PWM technique, and establish the voltage at the machine terminal such that the motor draws the current from the source which is this required current, that is IDS and the IQS, and the rotating frame of references are these ones. So if that set of current is drawn, so you can say that now your machine is is operating according to your requirement, that you are going to get the rotor flux and the required speed. Okay, so if you are going to measure the voltage and the current, and with the help of that you are estimating this cos of theta and sin of theta, and you are estimating the rotor flux, then this method of the vector control is said to be the direct vector control. The other method that I told is the indirect vector control. In this diagram you can observe the indirect vector control. So what we are doing over here, just look at this bar from the motor. With the help of the incremental encoder we are calculating this or measuring this theta r and the rotor speed, and we know that our current space vector, stator's current space vector, that rotates at the synchronous speed. So the synchronous speed is the omega e, because your frame of reference is rotating at that speed. And what that will be equal to? That will be equal to the rotor speed that you have measured with the help of this system. And then you are going to estimate the slip speed, and if you add these together you will get the synchronous speed. Synchronous speed is equal to the rotor speed plus the slip speed, right? So slip speed is estimated, right, that is omega sl over here, and the omega r is measured, and then you estimate the omega e, and with the help of that omega e you are going to calculate this theta e, and then you are going to generate this unit vector, that is cos of theta e plus sine of theta e, and then with the help of this information you are going to construct the vectors, reference vector, that is ia, ib, and ic, and you give it to your inverter over here, inverter control, and that inverter is going to realize that set of current in your machine so that you get the required flux and the torque component. So if you look at this part, you have the speed reference, right? From the speed reference you get the information of the required rotor flux, then you look at the actual rotor flux that is measured or estimated, and then through the controller you decide about what should be the d axis component of the stator current, because that established that rotor flux. And then if you look at this part over here, you are going to have the reference position, the actual rotor position, and then through the controller you are translating in terms of the speed, and then you are estimating or measuring the actual speed, comparing that, you are generating the error in the speed, and then after passing through the controller you are deciding about the IQS, the q axis component of your stator current. And with the help of this information, that is the rotor flux that is being fed over here, and so let's suppose this is being measured or being estimated from some block. Using that information you are going to estimate the slip speed looking at the machine parameters lm, rr, lr, right? So if you use the rotor flux information over here, you can estimate the slip speed, and with the help of that one you can estimate about these unit vectors. So we will discuss this diagram in detail in the upcoming videos, that we will drive this in complete form. So at the moment, the important thing that I want to explain to you, that is the indirect vector control. In the indirect vector control, you are going to estimate this unit vector with the help of the speed, the speed that you are going to measure or you are going to estimate. In the sensorless control, the speed may be estimated, right? So in the sensor control, you are going to measure it. So if you measure the speed and then you decide about the unit vector over here, cos of theta e and sin of theta e, that is used for the transformation from stationary to rotating or from rotating to stationary frame of reference, and establish a vector, reference vector for the electronic circuitry, power electronics part, and that power electronic part then realize that current. So then it is the indirect vector control, because you have estimated these unit vectors from the speed. In the direct vector control, you will be estimating these cos of theta and the sin of theta e with from the information of the voltage and the current. And definitely for all of this, you will be requiring very fast controller. Digital signal processing is used to calculate these cos of theta and the sin of theta, which implements the transformation. So in the upcoming videos, we will go into the detail of this direct vector control and the indirect vector control. We will drive a complete model for direct and indirect vector control, and we will also establish the simulation in the MATLAB to observe the direct and the indirect vector control. So if I summarize this video, we have discussed about the basics of the field oriented control, and we have discussed the analogy between the DC motor and the induction motor, and then we have seen that how stator current of the induction motor can be decomposed into two parts, one for the control of the torque and one for the control of the rotor flux. And then we have discussed the method in brief, that how we can implement the field oriented control. And then we have seen two types of the field oriented control: direct vector control and the indirect vector control. So in the upcoming videos, we will see field oriented control more in detail. That's all from this video. Thank you very much.